Okay. Welcome, everyone. Thank you for coming. I'm Yannis from Dedaub, and I'm going to talk about our technology for analyzing all deployed smart contracts. I'm going to tell you about some of the cool things we've been doing for the past year. Basically, I'm going to go over 3 stories of where our technology has come very handy, and hopefully they're going to be interesting stories. So to start with, I know this is not the best setting for interaction, but who has heard of Dedaub? Not many people, so excellent. So my talk is not going to go to waste. So who are we? We do research and technology in program analysis, and we've leveraged this for smart contract security. So we've become one of the successful security firms in the smart contract space, in the Web3 space. We've become a major auditor for many of the services that you know and love. We audit nearly everything from Chainlink, for instance, but many other organizations as well. We audited EigenLayer just last month. So we've been a pretty successful auditor. At the same time, we've been pretty successful in bug bounties. So we've disclosed many vulnerabilities. So since 2021, you may have seen some of these articles, but basically we've found 11, well, we've found hundreds, but we've gotten 11 bug bounties from vulnerabilities in deployed code. So we've received more than 3 million in bug bounties alone. So we've been pretty successful in this space. Now, but what most people know us for is app.dedaub.com or library.dedaub.com. It's the same application. It's our tool. People have started calling it just Dedaub. And it's a lot of things. It's an explorer that decompiles all deployed smart contracts and runs various analysis on them. Anyone who wants to explore contracts that don't have source code, for instance, comes to our tool. Anyone who wants to explore MEV bots or hacks or anything like that. And this is all based on our decompilation technology primarily. So we have the best decompiler for EVM bytecode. Smart contracts on any Ethereum VM chain, Ethereum, but also all its relatives. They are deployed in the form of EVM bytecode. We can reverse engineer that better than pretty much everyone else. So we are the leader in this space. Now, why is this interesting that we have a decompiler? Well, why do I care? I deploy my smart contracts, and my smart contracts have source code. Well, you care about having a decompiler because it offers a unified platform for automatically analyzing smart contracts. So the decompiler is just a great unifier that enables automation over the smart contracts. That's why you care. So what I'm going to do today is talk about where we've been invaluable in the space. And specifically, these are all stories from the past year. So generally, whenever there's a question that needs to apply to all contracts, all deployed contracts on Ethereum, but also other networks, Arbitrum, Optimism, Phantom, Base, etc., anything EVM-based, people come to us. So let's look at a few applications where our technology has come pretty handy. So story number 1. This was about a year ago. This was February of 2023. This was the finding that over 1/3 of deployed smart contracts have more than 50% of their deployed bytecode be junk code. So sometime a year ago, we tweeted this finding. There's a Solidity compiler, a Sol-C bug, that resulted in most code for many, many contracts out there, most bytecode being junk, never being used. So what's the bug? Like, how did this come to be? It's kind of an esoteric thing. It's a Sol-C bug where library code was only called in the constructor, so it's never used while the contract is running, but the Solidity compiler does not throw away that code. So it includes it in the runtime bytecode, in the actual code of the contract that goes on the blockchain, even though it was never used while the contract is running. It's only going to be called while the contract is being deployed. And this is particularly important for small contracts like proxies. So if you have little proxies that basically have this shape here, and I don't have a pointer, it seems, They have a constructor that calls a bunch of libraries, but then they have code that just forwards to an implementation, and they never need these libraries again. The code for this proxy contract will include all the libraries that are called in the constructor, even though they're entirely unnecessary. So this was kind of a surprising finding. This was fixed after our report in Sol C 0819. So this was a finding that leveraged uniquely our technology in the past year. Moving on to story number 2. The Ethereum Foundation often asks itself, what will be the impact of this improvement proposal, this AIP, on all deployed smart contracts? And whenever this happens, we are the natural people to ask. So we've done lots of studies for the Ethereum Foundation over multiple EIPs or things that don't even have an EIP code, like the upcoming Vertical Tree transition. All sorts of upgrades. We study their impact over all deployed contracts. So we are being commissioned to study the impact of all of that. And it's kind of interesting because the general pattern of this is to ask us which smart contracts are going to break if we apply this and that change to the EVM, and which of these contracts are important. And the important part we'll have to discuss because it's going to come up again and again. So that's also part of our technology, not just find what the contracts can possibly do, which is part of our static analysis technology, but also what impact will this have to the overall ecosystem in terms of tokens that are being held, in terms of importance of the code to other contracts, et cetera, et cetera. Now, this is important because upgrading the EVM is a pretty dangerous task. If you want to change the semantics of the EVM, it's like upgrading a car while it's still running. And that's exactly what the Ethereum Foundation has to do. And that's where these questions become particularly valuable. So in detail, let's say what we do is ask ourselves, if I get an upgraded EVM, let's call it EVM Prime, it runs smart contracts, and we want to ask, for all executions over all smart contracts, how many will break that didn't used to break before, and how many are important? And our technology comes to answer different questions, such as what is for all executions, what does it mean to break, and what does it mean to be important? So let's have an idea. First of all, for all executions. That's where we use static analysis technology. We have lots of research publications on static analysis. That's part of our DNA as a company. It effectively answers the question, what will a smart contract do under all possible conditions? So our particular technology starts from turning a program into a database. So you can think of it as the decompiled program on the left. It has a loop, and then we insert elements from the program inside tables, and you don't need to parse all of that, but think of it as having tables like induction var and flows and loop with conditions. So we represent now the program as a database, and then we can run pretty important queries, pretty convoluted queries over that database. So we actually use a language that supports recursion. It's called Datalog. So we have a logic-based language that queries this database and can ask things like, well, can you find me all the loops and their bounds, and if they satisfy certain conditions? And again, I'm not going to go into detail, but you get an idea of how we actually specify these algorithms from the little fragment on the left, which is a fragment of the query that we run on the database that represents the program. And then this will actually tell us, well, this program on the right has a loop, and it's bound by variable n times. OK, so this is how we answer the question of what is all executions. How do we answer the question, what is all interesting executions? Programs are one side of the coin, and actual executions of programs, transactions, are the other side of the program, of the coin. And what our technology does is also encode transactions as a database. So this is dynamic analysis. We go over all past transactions. We squeeze them. we distill them down to their essence, so to speak, and we go and store everything in a database that we can query pretty effectively. So for instance, a query may be, give me all the past executions of function so-and-so that have a fixed gas budget. When they're called, the gas that's being passed to the call is, say, 2300, so it's a bounded gas allocation. So when we have the technology, so we have the program as a database, we have the executions as a database, still to answer the interesting questions, we need to apply some ingenuity. And I'll show here an example from a recent study. And the study is over the question, does this smart contract, or find me all the smart contracts that have logic that parses RLP. RLP it doesn't matter too much, it's recursive length prefix. It's a particular kind of serialization, particular kind of encoding of data that's used for blockchain data. So effectively, this tries to find all smart contracts that analyze transactions over Ethereum or other blockchains. So it's kind of a weird thing. The contract itself takes in signatures of transactions and analyzes them. So how do we find this? Well, what we do is we come up with clever ways to use our technology, like static analysis queries over this question. So for instance, in this case, to find contracts that implement RLP decoder libraries, we'll look for specific elements in that code, like specific constants that are used in the RLP specification. And that's not too clever, that's pretty straightforward, but again, it shows that we use the technology and then we have to somehow be clever about how we query the technology. This part is a little more clever. If we want to find past transactions that actually had RLP encoded data, we came up with a clever technique there that basically says, I'll parse the call data and I'll see if I find a bytes array whose length matches what should be inside the array, which is also some length fields, in the case of the RLP specification. So this is kind of a clever query tuned to that particular analysis. Again, the point is not to discuss this query. The point is to kind of illustrate how we use this technology, which can answer all sorts of questions, to answer a particularly interesting question over all deployed contracts and past transactions. And putting it all together, we have all important contracts, we have all executions of contracts, all potential executions, we have all past transactions, and in the end, anything we report, we have to filter by importance of contracts. So we have to ask ourselves, well, we found all the contracts that may be affected. Which of them are important? Because there's lots of contracts deployed out there that have no importance whatsoever. They don't hold money, nobody transacts with them anymore. So what's the importance of a contract? Well, it's a complex question, but for instance, it could depend on any of these factors. It could be that the contract is part of a major protocol, it holds funds, it transiently holds funds, so has some privileges, some permissions with some other contract. It's used as implementation, and someone else who is important calls it, has approvals, et cetera, et cetera. So lots of criteria can tell us that the contract is important. And that's also part of our vocabulary. That's also part of our database technology that one can write queries over. And this requires fairly specialized data infrastructure, and much of this is actually showcased in our public tool. So if you go to app.dedaub.com, much of what you see is based on the exact same database that we use internally or as part of our security suite for program analysis of these kinds. So that's story number 2. These are the studies that we run for the Ethereum Foundation, find the impact over all deployed contracts. What's story number 3? Well, that's kind of the most obvious one. War rooms for major hacks. If there's ever a hack that can affect the whole ecosystem, more likely than not, we are being called in. So you've seen those movies that talk about extinction level events. Well, in this space, we talk about ecosystem level vulnerabilities, and that's exactly the same thing. Could there be a bug that will wipe out much of the value held in a specific blockchain? on the mainnet or on some other chain. And whenever something like that happens, whenever there's a threat discovered that's widespread, it's not limited to one protocol, we can participate, and we often participate in war rooms, to apply the same technology and expertise as in the Ethereum Foundation studies and help answer the question, who is affected? So, very recent example from a couple of months ago, from December of 2023, the ThirdWeb vulnerability. You may have seen the disclosures from OpenZeppelin. There's a bad interaction between a couple of libraries that implement the 2771 standard and multicall. And if you saw the post-mortem, we're being credited there for the crisis management, for the queries. So what did we do there? Basically, again, same pattern as what we did with the Ethereum Foundation studies. We ask ourselves, what are all the affected contracts out there? How did we do it in this case? Well, in English, it looks a bit like this. For all contracts that contain these elements in their decompiled code, so they contain a delegate call, they contain some specific call data array manipulation that indicates a trusted forwarder, which is part of this attack, of this vulnerability, and they also support a certain interface that indicates multi-calling. Find the contracts themselves, and if they're implementation contracts, also find their proxies, including diamond proxies, and report the union of all of those. Every single step I defined here, every single step I presented, uses one part of our technology. It uses the decompiler, because we want to unify all deployed contracts to find these code patterns, regardless of what they've been compiled with and how exactly they specify it in the source code, whether they use an extra parenthesis or something. So we normalize everything. We match patterns on the decompilation. We check signatures. That's also part of our technology. We check in our database all the relationships between contracts, whether we have proxies, whether we have diamond patterns, everything. And then in the end, we also need to ask, what are the important contracts? And I'll get back to that in a second. But let's, just to give you an idea, just to give you a glimpse of the technology and what it looks like internally, which is also the same language that you can use for monitoring bots in our system, if you are a user of our integrated security suite. Here's what the query looks like. Now, again, I don't think you can parse this very quickly, but this is the same thing that I described before in English. So it basically looks at the specific patterns in the decompiled code, and then it queries the database for all proxies that call contracts that have these patterns, including all diamond patterns that may involve the contract that has these patterns in. So that's what we actually did for the ThirdWeb vulnerability 2 months ago, and we combined this with important contracts, because if you just run this over the 800,000 different code bases that have been deployed on Ethereum alone, you actually get over 10,000 contracts that are potentially vulnerable. So you have to ask, what are important? Which ones are important? So again, you have to combine it with, is it part of a major protocol? Does it hold funds? Does it have permissions? Does it have approvals? Is it involved in some way in something that could control a lot of funds? And in the end, that's what human inspectors analyze. So we report a small subset of the contracts, and people go in and they analyze them for vulnerabilities with manual inspection. So that's all I had to do, I had to say. It's basically, I took you over our unique technology strengths, and I kind of gave you examples with these 3 stories from what we've been doing for the past year. And the main idea, again, is we have technology to normalize deployed smart contracts so we can run automated queries over them. We do the same for transactions, and by combining the two, we can capture a lot of the potential for either bad effects of vulnerabilities or of the potential for anything that could happen when a contract or the Ethereum VM itself evolves. Thank you very much.